So do you want to see your tests briefly and then give them back to me, or just wait? Because I can't talk about solutions. I haven't posted anything yet. But if you're dying to know what your score is, I can show it to you. And then flip it over. Give them right back. Just to look at, I haven't entered the score yet. Why? I tell you why. The handout got screwed up. You can look at it for a little bit longer. I'm going to make you. You have to hand this back because I haven't recorded the score yet. Okay. I redid the handout. The second handout with pictures. Oh, wait a second. take this back. Total 105 points.
Okay. Is it true that if you have a magnitude of class, you got a more
you have to take the final, but it won't count. That's my official policy. Because I want you to practice questions, practice the problem solving is another way of anchoring it. You should study for it, you should review, you should do all that stuff, but you don't have to worry about it as much. If you got other priorities, you can focus on those. But I want to make sure that everybody leaves this class having a solid grounding in the subject matter. So, yeah. Anyway, I just scrambled to redo the handout for friction. And also, I finally downgraded my office to 2013 so that hopefully we're not going to have this frickin' notation issue all the time. And we're working on friction again, kind of slowly. We're recording, good. No, I don't want presenter view. So a quick review up to this point. We've been working on friction for quite a while. I was going to do a little demo today. I just can't get it together. You guys got so many things going on right now. You know, we talked about this friction as being a force that prevents motion, and we look at, you know, questions on whether a crate will slip given the circumstances of the problem, and we set up the free body diagram. We have this friction force, and what's the direction of the friction force always? What is the direction of friction? Perpendicular to the surface? No, that's the normal force. What's the direction of friction? Yeah, it's the direction opposing motion, the motion that's about to happen. And that could be, in this case, the crate's about to slide down the ramp, so the force of friction is pointing up the ramp, right? So it's always opposite of the direction of sliding, right? If you're pushing on this refrigerator to the right, friction is going to push back to the left, keep it from moving, right? And in some cases, if you push high enough on a tall rectangular object, it might actually tip instead of slip, and that's the other issue. Having this extra force creates an extra unknown, and that gives us too many unknowns to solve, right? Because the equations of equilibrium only allow us to solve for, like, you know, with a 3D problem or a coplanar problem, whatever is, we only can do like 3 unknowns. Well, if we get this friction force, we have another unknown. We can't write any more equations to kind of solve all those things. So what we do is we make assumptions. We assume that it's, you know, that it's in equilibrium, and then we see, well, can the friction force, you know, maintain what it needs to be in equilibrium? And if it's not, if it can't, then it's going to be moving. Or maybe it actually satisfies force equilibrium, like, so for this refrigerator, we have this force equilibrium equation. And, you know, we can show that it doesn't slip because the friction force is able to withstand that P, right? Because, and what's the maximum friction force can be? Ollie, what's the largest force that friction can get to? Nope. Isaac, what's the largest force that friction can get to? 70? Matthew? Largest possible force? Yeah, there's this thing called the coefficient of static friction and times the normal force, right? Okay, the normal force is, in this case, it's the weight of the refrigerator, or weight of that crate, right, which is 400 pounds. And so the coefficient of static friction is given as 0.35. So what's the largest friction force you can have on that crate? 400 times 0.35. If it was 800 pounds, the friction force could be twice as big, right? It's a lot harder to move something that's twice as heavy, get over that friction, right? So, but, even though the crate can withstand the friction, the friction force can meet that force of 125 pounds applied there. What also happens when you start pushing on a rectangular box is the normal force starts to slide because you start getting a couple here, right? If you push on this box with P and friction is opposing at F down here, you've got a clockwise couple. In order to keep this thing from tipping over, we have to create a counterclockwise couple. That happens by the normal force where it's effectively applied, and this is a distributed load, but we have the effective load because it's sort of a trapezoid. It starts shifting to point A, shifting to the right. And that presents a countercouple to keep the thing from tipping over. Right. What's your finger doing on the mouse? Guarding you guys, you got to stay focused. And what happens is if that point goes too far to the right, there's only a certain distance that normal force can slide to the right. If it goes past that, Jose, what happens? It's going to tip. Yeah. So we make another assumption that, so even though, the friction force can meet the static equilibrium for forces, it may not be able to meet the static equilibrium for moments. Now we can do the moment equation, Wx, the weight times this distance x, that's how far we are away from the center line, gives us a counterclockwise moment minus p times 8 gives us a clockwise moment equals 0. We can solve for x, this other unknown, right, which then equals 2.5 feet. In that circumstance, 2.5 feet is beyond the right corner of that crate. Therefore, the crate is actually tipped over. This is sort of the summary that we've done. It's all in the previous videos. We did impending motion at one point. Then the question is, this is sort of an interesting question. Impending motion is when you're right at the verge of this thing moving. And again, friction always opposes impending motion. And this is the case where the crates, we want to know, okay, not whether the crate's going to slide down or stick, but we want to know what's the minimum force we got to apply to prevent that crate from sliding down. And in that case, impending motion is down. So friction is up. Friction is helping us. If you're trying to keep this thing from sliding down, you don't have to press as hard as you would if there wasn't any friction. Friction is helping you. Okay, you set up the equation, you solve for that. Conceptually, that's pretty straightforward. What about the minimum force needed to push it up? Well, now friction is fighting you. So you got to push extra hard than if there wasn't any friction, right? And you can see the difference. It only takes 56.7 pounds to keep the crate from sliding down, but it takes 143 pounds to make it actually go up. That's a lot, 100 pounds extra to make that thing start going up, right? That's the difference that friction makes. And you can kind of plot the magnitude of F, and these forces, so if the P that you're applying is less than 56.7 pounds, if you're in this region, then the crate's going to slide down the ramp, right? But if you're in this spot here between 56.7 and 143, what happens in that period between 56.7 and 143? What's the crate doing? It's staying still because you haven't overcome enough the friction force to make it go uphill, and it's not minimum enough to make it slide downhill, so it's actually stationary right in here. Until you get to 143, then it actually slides up, right? You can sort of run that through your head and see that sort of makes perfect sense. Next time you're trying to keep some big sack of potatoes from sliding off your ramp or something, I don't know, you can think about that. We wrapped up last Thursday with the idea of a ladder, a guy on a ladder, and we want to know what's the minimum angle for stability. Sometimes these questions are worded wrong. And in this case, the slippage is going to happen. If this ladder slips, it's going to happen at B and at A, and we have to write the equations to solve that. And it turns out you get an equation involving theta, which is not, it's not something you can actually solve analytically, but you can guess and check and find that theta is 55.6 degrees. And that means, you know, if the angle of the ladder is less than 56.5 degrees, somebody who stands on it is going to find the ladder slips down and away from the wall, right? So all that pretty fascinating stuff, and you can go back and pick that up later if you missed some of that. And then I noticed some of these problems were not in the handout, so I'm adding a few more things here. And yeah, we're gonna, it's kind of good, you know, friction is kind of a long topic. There's a lot of different facets to it. And this way, by spending an extra week, I think we're gonna have a better sense of it, hopefully. And I hope not to talk too long to get us solving problems. But again, to kind of get you in the feel of it, these are other types of problems you might run into. And again, this is all for mechanical engineers. If you're a civil engineer, I don't think this is going to really be too helpful for you. Okay, sorry, but it could. You never know. But here's the situation, and we're going to look at these kind of things. We're going to look at wedges, another mechanical engineering thing. We're going to look at belts, belt friction, and pulley friction. So those are the remaining things we're going to look at in friction before we kind of dive into the problems. Anyway, yes, so we want to know, the question is what force P is needed for motion, just to get anything to move, and will block C actually slide? So again, you start thinking about all these possibilities. You could have, depending on the friction coefficients, you know, when you start pulling that thing, what's one option? B could slide out, leaving A and C where they are, right? Or you could imagine, suppose there was no friction at this boundary right here, and you start pulling at P, what's another thing that might happen? Ollie, was it? Sorry? Yeah, B and C might move as a block, right? They might be sort of stuck together from friction and slide out, right? So again, we have to sort of reason through all those situations to figure out which one actually happens. This is sort of, that friction is kind of this exploration. It's a more complicated sort of process. It's sort of, this is kind of how, I don't know, in some ways kind of circuits work. Kind of, there's all these different ways of kind of looking at things and kind of explore these things. Circuits is more challenging than statics. And this is, friction is sort of one of the more challenging statics problems, static theories. So we look at this and we think about case one, where B slips at both surfaces. And we draw the free body diagram. And what that free body looks like is we draw it for the different parts, right? Now, this is a kind of a gripe I had. A lot of people were doing free body diagrams that weren't really free bodies, you know, and so I marked people off for that. If your free body diagram showed all the stuff that's hooked up to that, it's not really a free body diagram. And it's confusing when you try to solve it that way. So I've been hammering this all the time. So I want you to kind of try to, free body diagram of B means that it's just B. Free body diagram of A means that it's just A. So we can diagram both A and B here. Notice they're not connected to each other. These are two distinct free body diagrams. The only thing that is acting on those bodies is forces. There's no other block attached to it. There's no rope on it. It's just forces acting on that body. That's what a free body diagram really means. Okay, so So we have a weight force, the force of gravity acting in the middle of that box, right? And what else is acting on that? Tension. Yep, we can say there's a tension at A. There's not a rope there, it's just a force. That's all that thing is feeling, right? That's what happens when you make a free body diagram. And what else is acting on it? Normal force. And this normal force is at the boundary of A and B, so we can call it NAB to distinguish it from some other forces, other normal forces we might run into. And then which direction is the friction force acting on A? To the left or to the right? To the left, because A wants to move to the left, right? No. Which way does A want to move? If you start pulling up B to the right, which way is A going to want to move? You said left. A wants to stay on the left. Okay. Well, suppose the rope wasn't attached to A, and we start pulling at B. What do you expect to happen? Which way is A going to go? It's going to go with B, which is to the right, right? What force is making it do that? The frictional force at the boundary between A and B, right? The friction force wants to make A go which way? When you start pulling on it at P, which way does A want to go? It wants to go to the right, right? What if this rope was loose here, right? Right, and you start pulling, it's going to get taut, right? Because there's something pulling it to the right, and that force is friction. It's the friction force pulling that thing to the right. I know this is kind of weird the first time you see it. Requires a lot of introspection, and you got to imagine these things, right? So the friction force from A to B is going that way. Well, this sort of makes sense, and remember, these are like internal forces from a larger perspective, right? So that on the other end of that boundary, they're going to be equal and opposite, right? So the normal force AB acting on object B is going down. Which way is friction acting on B? Yeah, left, right? It wants to keep the block B from moving. And we're trying to move the block to the right, so the friction force is against the force of the direction of impending motion, so it's going to the left. Okay, we have our force P applied, right? And we also have a normal force at this boundary BC. And which direction is friction force acting at that boundary? Left. FBC is also going left. Okay, that's the free body diagram. If you can do that, that's the first step of getting these problems solved. If this is really hard, that's where you're going to have to kind of focus your efforts to kind of clarify these things, right? These are really, I can see a lot of the problems we're running into a lot of people were running into problems on the test because they weren't able to do a clear free body diagram. They ended up doing some really crazy things because of that. So block A then, we can sum all of the forces in the y direction. We have to just sort of explore this system now. So we're starting at block A because we kind of know a little bit what's going on. We know each block weighs 20 newtons, and the coefficient of static friction is 0.25. So the y forces on block A are NAB minus WA, so we know right off the bat that NAB equals 20 newtons. Some of these forces are trivial. And we're really kind of interested in what's going on at block B, so we're going to now focus on that. Now that we know what NAB is, that's one of the forces acting on block B as well, right? So we can find the sum of the Y forces. And that's going to be NBC going up, right, minus NAB going down. Minus WB. Oops, there's a weight. Got to add another force on this thing, adding a WB to block B, right? Its own weight. And therefore, we can find that NBC equals 40 newtons, right? Just by the fact that it's got 2 blocks above it, right? That's what that normal force is dealing with. Yep. Would block B also experience the weight of block A on it? Yes. That's what NAB is. NAB on block A is, so if you think about it, right, NAB on block A is the force that block B is exerting on A to keep it from falling due to the weight of gravity. So it's opposing the gravitational force, right, keeping that thing in equilibrium so it doesn't move vertically, right? That's what the normal force is doing. It's counteracting the effects of gravity. Well, that force that B is applying to A is also what A is doing to B in the opposite sense. A is compressing B by its own weight of 20 newtons. We call that NAB still. That's how that's taken care of. It's those normal forces. Good question. It's those normal forces which are taking care of those weights. Okay, so NBC is 40 newtons, right? It's got 40 newtons to push up because there's 2 blocks above it. Makes sense, right? And some of these things, you know, once you do a few of these, you don't have to write these equations. It's kind of obvious. But until you get comfortable with it, you should write these out because this actually keeps your work very systematic and clear. So the X forces, we've got P going to the right, and we've got a minus FAB and a minus FBC. Okay, but this is the assumption, right, that B slips at both surfaces. So what do we know about when B slips at both surfaces? What does that help us pin down for the friction forces? If it's slipping at both surfaces, what does that mean about, what can we tell about what FAB is? So we're going to make these friction equations. They cancel each other, nope. If it's moving at both surfaces, what do we know about FAB? What do we know about FBC? It's impending motion. What does that mean? Ollie, what does that mean? Yeah, that's the largest force the friction can actually be, right? See, when this is sort of what we're going back to this thing here, right? When you're in this region here, the magnitude of F is less than mu s times the normal force. And that the friction force doesn't always stay at mu s n, right? If it doesn't need to, it's not going to be any bigger than it needs to keep it from moving, right? So when the magnitude is less than mu s n, then the crate is stationary, right? But when you're at these transition zones, this right here is the point of impending motion. If you go beyond this point, it's going to start moving, right? If you go below this force here, it's going to start moving. Those are key points on that friction curve. And so we like to track those. And when this thing is starting to move, you're at those points where you just got past that threshold where it's going to start moving. So the FAB is mu s times, or just mu, times NAB, right? And what about FBC. If it's moving at that boundary, what does it must have to be as well? It must have to be mu times NBC, right? So you plug these in. You know what NAB is, you know what mu is, you know what NBC is, and you know what mu is. So this tells you the answer in this case. You can solve this without too much trouble, right? These are not algebraically very hard. If you set up these free body diagrams correctly, these are actually pretty easy to solve. Just kind of grind through these things, right? And this will tell you that P equals 15 newtons. This equation, coupled with those friction equations, is going to tell you that P equals 15 newtons, right? You can figure it out pretty easily. Because a quarter of 20 is 5, right? And a quarter of 40 is 10. 5 and 10 added together is 15, so P is going to be 15 newtons. And I went through the first slide in a whole year without having any jerky marks. It's been a traumatic year for me. I'm so happy that it's over. Well, that was just case one of this long-winded problem. Now, the other thing we got to explore is, well, what happens if B and C stuck together for some reason and the whole thing moves as a unit? What P would that require? And then whichever P is smaller is going to be the one that actually happens, right? We have to explore both of these situations and find out which one is smaller, because that's the one that's going to happen. So the idea is we start by, consider the situation where P equals 0, and obviously the blocks are in equilibrium. And the idea is we're going to just increase P until something happens. Not yet. But this is the reasoning I just said. We're just increasing P until something happens. In the case with the lowest P, will occur first. There's no dot over occur, but I put one. So we're going to now explore case 2. Blocks B and C sliding together. And so again, we draw the diagram for A. Which is the same as it was last time. And oops, friction force should be lower. So that's the same. And then we draw these boxes B and C like they're fused, because we're assuming the slipping is going to be taking place at that other boundary, not at the boundary between B and C. So this is the combined B, C unit acting as one thing. We've got a normal force at A and B coming down, and NAB, not the normal force at A and B, NAB coming down, which is the weight of A. We've got that FAB also still trying to keep us from moving. And we've got a total combined weight of gravity as WB plus WC. And then we've got a NC CD pushing up, keeping everything from falling, and an FCD here that we would also have to overcome with our P force acting on B. So again, looking at block A, the sum of the Fy's equals 0 is NAB minus W sub B. So again, NAB is 20 newtons. And then we look at blocks B and C taken together. And we say the sum of the Fy equals 0. Again, now we've got an NCD pushing up minus the NAB minus the weight of the two blocks. So NCD has to be 60 newtons because it's got the weight of 3 blocks to push up, right? Could have done that by inspection, but just cranking out those equations always sort of helps clarify things, right? The normal force at D, right, this point here, this has to be supporting 3 blocks, so that obviously has to be 60 newtons to keep those things from falling, right? And again, the sum of the FX's, it's the same setup as last time, just different variables. So just P minus FAB, well, that's the same. But now we've got minus FCD. And FCD, with the friction equations that we did last time, is, again, we're at impending motion, so FAB equals mu NAB equals 5 newtons. And FCD equals mu NCD, which equals 15 newtons. So we plug those in, and this tells us that P equals 20. Newtons. So based on this reasoning above, that, you know, if we start at 0 and we kind of slowly increase P, blocks are going to stay in equilibrium until something happens. The first thing that's going to happen is B is going to slip out between A and C, right? It's going to slide right out between the two. So block B slips when P equals 15 newtons, and C does not slide. So that's our total reasoned conclusion. Okay, questions? Well, those are the basic problems in friction. And then what comes next are things where you start to get more interesting systems of blocks and stuff. It's a small step to go from 3 stacked blocks to a wedge, where now 2 of the blocks are cut at an angle. And this forms the basis of what a wedge is all about. And we use wedges all the time, like door stops are wedges, right? You jam them in there, and those things are considered self-locking if, you know, they can keep the motion from happening without you having to apply any force on them at all. Or like you try to, like with a door stop, when you have the door stop in there, right? If you try to close the door even harder, it jams it even further. It's just really stuck there, right? You try to yank on it, that's self-locking. You know, no matter how hard you try to push it, the door against the doorstop, it ain't gonna move because that wedge has got it firmly embraced there. Right? So wedges are dealing with impending motion at all points. And there's this mechanical advantage of WA over P. So the weight of the thing that you're trying to keep supported over like the P force that you might need to support it with is a mechanical advantage. So if this is a 100-pound crate and it only takes you 10 pounds to keep it from sliding down, 10 pounds of P to keep that wedge from popping out, right? This is not the same as a doorstop. It's a little bit of a different scenario, but it's the same kind of idea. Then you've gained a factor of 10 mechanical advantage, kind of like those pliers, you know, if you can apply 10 pounds of force, but you get 100 pounds at your plier teeth, jaws, then that's called a mechanical advantage. This notion of self-locking, though, similar to a doorstop, is that if the P, you know, if the P needed to prevent B from sliding to the left is less than 0, that's considered self-locking. In other words, in order to get that crate to slide down, you would have to pull the wedge out as opposed to pushing it in. In other words, if nobody's messing with that system, the wedge is supporting the box as it is without any additional force required, right? And typically what we're doing here, and you've got these things drawn, right? So on your handout. So the situation might be, we might be asked to find the minimum P needed to keep the crate from sliding down. And let's look at all the forces acting on A. Who can tell me one of the forces acting on box A here? Ollie, force acting on A. Just one force each, right? So you said the normal force, and what are we going to call it? Say NAB maybe? Okay, Isaac, another force acting on crate A. Frictional force between B and A. Good. In which direction is that going? Opposite of B, opposite of P. It's trying to push back, right, and trying to keep the crate from sliding down. And if the crate did slide down, yeah, friction is helping us, right? The impending motion, it's actually easier to figure these things out at the wedge. If we're trying to keep the minimum P to keep the crate from sliding down, the wedge, impending motion would be, which direction for that wedge is impending motion? This wedge at B, it's not going to be really down. I guess down, you could sort of call it down. I would sort of call it going this way, right? Right, I mean, if you take the P away, the idea is the wedge is going to pop out, right? Impending motion is going to the left, right? So friction acting on B is going to the right. Friction is helping you, right? FAB. And what Isaac said is correct. The friction acting on the box at A is going in the opposite direction of that. It's going to the left. Okay, but there's another surface here. And this vertical surface, we also have to consider the friction forces acting there. If we're pushing on it at P, that crate is rubbing against that surface. So there's more forces on here. There's a lot more forces. 70, can you give me another force acting on A? The weight of the crate, right? W sub A, right? Matthew, another force acting at A? On A? Yeah, there's gonna be a normal force coming from the wall. And if we're pushing at it with P, the normal force is gonna be pushing back to keep it from going into the wall, right? And we're gonna call this NA. David, another force acting on the crate. There's one more. Friction from the wall, which way is it going? Up. It's trying to keep the crate from sliding down, right? Which is the impending motion direction for the, so impending motion for A is sort of down, right? Impending motion for B is sort of out. And so that, again, the friction force is always in the opposite direction of impending motion. Olive. Read the question. Again, here, did you write this down on your notes? Are you writing these down? We're considering the minimum P to keep the crate from sliding down. Okay. So the other question, there could equally be a question, what's the minimum P to make the crate start sliding up? That's going to be a different problem though. In that case, all the friction forces are flipped. Yeah. Okay, 1, 2, 3, 4, 5 forces acting on A, and then acting on B. There's also going to be an NBC at this boundary, and a friction force FBC acting along that line, right? So to solve these kind of questions, you basically kind of start at A, because that's sort of a, you know all the, you can kind of figure out those forces. So for A, we're going to write, the sum of the Fx equals 0, and the sum of the Fy equals 0. For B, we're also going to write the sum of the Fx equals 0, the sum of the Fy equals 0. You've got that 15-degree angle there, so some of that normal force at B on the bottom is going to be giving you a horizontal force. Impending motion, though, says that all of these friction forces are at their limit. FA is at its largest possible value. FB is at its, or FAB is at its largest possible value. Impending motion, yes. If it's not impending motion, they could be, anything that needs to keep it from moving, right? Which might not be that big, but those are the maximum values of friction force. And FBC is equal to mu NBC. That helps reduce the number of unknowns, right? So we end up getting 7 equations for 7 unknowns, assuming W is given. And the unknowns are, we've got to find P, FA, and A, FAB, NAB, FBC, and NBC. So we're going to look at one of those, I think, in the in-class exercises eventually. So we're going to have another lecture tomorrow, but a briefer lecture to kind of wrap it up, and then we'll start doing some problem solving. The other 2 things we're going to look at are on the next handout, I believe. This is on, we got to the end of the second one, right? That's the end of wedges, right? So what's coming up tomorrow is we're going to look at belt friction and pulley bearing friction. And what's all that about? And then we'll be applying it on these system problems, right? These are interesting mechanical systems involving friction, where you've got 2 blocks, a pulley and a peg, and all those things have friction forces involved, and how you take apart a complex system, a complex mechanical system, and analyze the different friction forces in there to figure out what's the minimum P that you need to get one of those things to move. That's tomorrow. Thank you.